Hi, Physics 100. This is Dr. Ricardo. I had promised you I was going to do one of the harder circuits from your lab simulation. This was lab 12 in Physics 100. So it was circuit number 4. So the directions to build circuit number 4 is you have a 100-volt battery in series with a 50 ohm resistor that then splits apart into two parallel resistors, R2, which is 10 ohms, and R3, which is 30 ohms. So everything you see here in pen is what's given to you in the problem. So what I did was I just made a little summary table. So when we get our results, we can put them in here. The resistances are originally given you, okay? And down here, I just put the total. Now, since this is a circuit that has series and parallel, it's going to be a little bit complicated to figure out what the total resistance is. I can't just add these three numbers up and get 90, right? So 50 plus 30 would be 90. That's what I would get, plus 30 plus 10 is 90. That's what I would get if I took this 10 out of here and kind of put it down here so that I'd have to go all the way around one path. Remember, in terms of the current at least, the current has to split apart, and some of the electrons are going to go this way and some of the electrons are going to go this way, and then they're going to meet back up. Okay, so a couple of things that we do know. We don't know the total resistance yet, but we do know the total voltage, because the total voltage is the voltage that's provided by the battery. Okay, so that's something that you can fill in right now, right? The voltage provided by the battery is going to power these three components. So you can think about them in your house as different appliances. So you could say, okay, here's the toaster, here's a vacuum cleaner, and here's someone who's using a blow dryer. And if they're all doing this, what is the amount of current that goes around? What is the voltage drop across this resistor? What's the voltage drop across this one? What's the voltage drop across this one? So we're going to calculate that for each of the three components. What's the voltage drop across it? And what is the current going through it? Okay, so first thing we need to do is calculate RT. So RT, we're going to calculate by doing the something really kind of neat. And that is, we need to consider what would happen if we replace these two resistors that are in parallel with each other with one resistor that has an equivalent resistance in between them. So basically, what would happen if I figured out what would the resistance be if I replaced these two with one that has the comparable resistance to it? So that's what I need to do. So the first thing I need to do is ask myself, okay, what's the total resistance of two resistors that are in parallel? So take care of these two. So I know the formula for that. That's 1 over R, whatever you're talking about. So I'm going to call it R23 because it's the one that would replace number 2 and number 3. So 1 over R23 is 1 over R1, or excuse me, 1 over R2 plus 1 over R3. Okay, so I have two resistors that are in parallel with each other. I need to take 1 over 10 plus 1 over 30. So I can write that over here. That's equal to 1 over 10 ohms plus 1 over 30 ohms. Okay, so how do you do this? Well, you have to do the division first and then add them up. So I get 1 over R23, which is the replacement guy, right? So I'm going to call this R23, okay? The resistor that would replace those two. So now I would have a nice, easy circuit that I could just add up. Okay. All right, so that's going to be 1/10, right? Oops, sorry. Not in the denominator anymore. 1 over 10 is 0.1. And 1 over 30 is 0.033, but I'll show you that. 1 divided by 30. 0.033. Okay. 0.1 plus 0.033, you can just add those up. 1 over R23 is equal to 0.1333. And then the last step, if I don't want 1 over this number, I want R23, I need to flip over both sides. So take 1 over that would give me R23, and then 1 divided by that number would give me the result. Okay, so I'm going to take 1 and I'm going to divide it by my resistance, right? What's my resistance? 0.133. Okay. I get 7.52. Okay. And to 2 significant figures, because these guys only had 2 significant figures, I can just stop at 7.5. So it's 7.5 ohms. Okay, that means that, got one more step. That was the hard part. Here's the easy part. This guy who does the replacing, right? Let's connect them back up. Is equal to 7.5 ohms. So a 7.5 ohm resistor is equivalent to a 10 and a 30 in parallel, which makes sense, right? The total resistance when you have 2 things in parallel is always going to be less than whichever one is the lowest, because even though this 30 isn't so great, it's the harder pathway, it's 3 times harder than this pathway, it still helps, right? If you have a bunch of cars driving down the road and you all of a sudden have 2 lanes, some can go this way and some can go that way. So you take a log jam off, right? You take some of the pressure off of the circuit by having an alternate route, this other route over here. All right, so now what's RT for the whole circuit? RT for the whole circuit is just 50 plus 7.5, because now these 2 things are in series, right? Nice, simple, all the way around and back. So the total resistance is 50 plus 7.5. Okay, 50 plus 7.5, and I can put that number down here. That's 57.5. Good. And all of these guys, I won't put the units because they're all in ohms, right? Okay, so the next step that you should do is, you can take this off, you don't need that anymore, is ask yourself, what's the total current? So if we know that V is always equal to IR, then V total is equal to I total times R total. Okay, well, the total voltage we know is 100 volts because the only thing ever providing voltage is the battery. So whatever the voltage of the battery is, that's your total voltage. We now know the total resistance is 57.5, so I can get the total current just by rearranging this equation. I total, and I'll tell you what I total means in a second. I total is equal to V total over R total. Okay, here goes the numbers. 100 divided by 57.5 ohms. This is going to give us a unit that is going to be amps, right? The unit for current is amps of current, which is coulombs per second, right? Moving electric charges in coulombs around in a circle. So 100 divided by 57.5. Okay. That gives me 1.739, which is 1.74. 1.74 amps. Okay, now here's where that number applies. It doesn't apply everywhere in the circuit because we have a parallel section. Anywhere where the circuit comes together and there's only one pathway, there's only one way for the electrons to go, all this whole section in here, this whole section in here. In the simulator, you're going to see the electrons moving faster all the way in this whole section. The current through that whole section is going to be this current, 1.74. Why? Because there's only one way for the current to go. So if I think about it as electrons moving around, electrons are repelled from the electric part of the battery and they get sent through the circuit. How many of them approach the first component, R1? 1.71. All of the current is going this way. So I got 1.71. There's no choices here, right? All of the current has to go through this resistor. So how much is going through that resistor? 1.74 amps of current go through that resistor because there's no choices. Here, it's going to split into two different sections, right? Not all of it has to go this way. Some is going to go this way and some is going to go that way. Okay, so what you're going to have to do is you're going to solve for those in a minute. Okay, okay, so you're going to solve for those in a minute. So the first thing we can do is we can put this guy down into the table down here. This is what's going through R1 is 1.74. Okay, what's the voltage drop across that component? Well, if we know the resistance in the component and we know the current in the component, then we can use the voltage drop across V1. I'll show you down here. The voltage drop across V1 is the current times the resistance in that component. I know the current, 1.71. I know the resistance, 50. So I actually just have to multiply those two numbers. So V1 is equal to 1.74 times 50 ohms. So V1, the voltage drop, and I'll show you what that means in a second. The voltage drop across the first resistor, R1, is 50 times 1.74 equals 87. Wow, so that's a huge number. 87 volts gets dropped right at the first one. So I've got 100 coming out of my battery. 100's coming out of my battery. I lose most of it through here. Why? Because this guy blows away the other two. Look at that resistance. The higher the resistance, the more potential you're going to lose. This is the hardest part of the hill. I've got a total resistance of 57, and 50 of it is going through this component. So I've got a hill to go down. That's 57 feet high, and I do 50 of them right here. So this guy is going to be by far the highest voltage drop. So out of the 100 volts, you're going to drop 87. Okay, so this guy over here, I can write it over here. This guy has a voltage drop of 87 volts. Okay, so what would that mean? If I take my nice voltmeter, right? Take my voltmeter, it would mean me touching this side and this side. And if I want to get this to be a positive number, the black is the negative. I'm going to touch this side to the black side, right? That's the negative side of the battery, right? That's the negative side of the battery. And I'm going to touch the other part on this side. So if I measure the potential difference across this particular component from there to there, and I look at my voltmeter, what's it going to read? 87 volts. Wow. Okay, I wouldn't want to put my finger across there. If I want to measure the current through it and see that 1.74, I can't measure across, I have to measure through. So what you have to do is you would have to break the circuit and put the current meter actually inside the circuit, right? So that the electricity would travel through it and go through the other side. That's why for your simulator, you had that special kind of coil that just measures the current by measuring the magnetic induction, and you just put the coil around the outside of the wire. If we were doing this in lab, you'd have to break the circuit, put the current meter in between, and then read it. The current meter becomes part of the circuit. I would put it right here and measure the current in between. Okay? All right. So how much is coming across the outside in terms of current? Well, if 1.74 is going in, and there's only one pathway, 1.74 has to come out. There's my 1.74 up to this point. Now, it's going to split. Some is going to go down this way, and some is going to go this way. More is going this way compared to this. Why? Because this is an easier pathway. So if you want to do it in your head real quick, you can say, hey, what's the total choices? I've got 30 over here, and I've got 10 over here, so I've got 40. So 10 out of 40 goes this way. 10 out of 40, and 30 out of 40. Then the last thing you do is you want 75%, 30 out of 40 going the easier way, right? 30 out of 40 goes the easy way, and 10 out of 40 goes the hard way. Now, I know what you're thinking. You're thinking, wait a minute, the 10 is over here. Yes, you do have to flip it, because remember, resistance is in the denominator. But in the end, we're going to be able to calculate these numbers, okay? But in the end, you'll see that 75% goes the easy way and 25% goes the hard way. If these two had the same resistance, half would go this way and half would go this way, because one pathway wouldn't be harder than the other. They'd be equal to each other. Okay? But we have one that's 3 times easier than the other, right? 3 times easier than the other. 1 to 3. Okay, so first thing that we could do though is let's calculate what the voltage drop is across here and here. If I have 2 resistors and they are in parallel with each other, then the drop has to be exactly the same across it. If we know the total voltage of the battery is 100 volts, okay, and we've already used up 87, that means this drop has to be 13 and this drop has to be 13, because I only have to travel around the circuit one pathway. If I choose to take this route and I drop 87 and then I drop 13, I make it back to 0, because what's the potential difference between this side and this side? The potential difference is 100. So drop, voltage drop of 87, and we've just figured out that this guy V2 has a voltage drop of 13 volts. Okay? This guy also, V3, has a voltage drop of 13 volts. Now you're saying, what are you talking about? They have 2 different resistances. I don't care. Anytime you have 2 resistors that are in parallel, the voltage drop across them has to be the same. It's the current that's going to be different. So we can fill out a whole bunch more stuff in our table. We've got 1.74 over here. We've got 87 over here. Okay? Now, I know the voltage drop here and here, because they're in parallel, have to be 13. How did I get that 13? 100 minus 87, because I know if I put back the equivalent one, I always have to go around any pathway. 87 plus 13 volts has to equal, this is gone, right? 87 plus 13 has to equal 100 volts. In a simple series, you can add up the resistances. 50 and 75 and 7.5 gives you 57.5, and you can add up the voltages. Okay? So this guy has to have a voltage drop of 13. Last time I'll say it, anytime you have 2 resistors in parallel, the voltage drop across them has to be the same. Okay, think of yourself going on a hike. If you're going on a hike with a friend and you say, oh, I'm going to go this way, and you go that way, and I'll meet you at the bottom. We'll meet right here. Well, yes, maybe this person had a longer pathway, but the drop, the altitude difference from the top of the mountain to the bottom of the mountain has to be the same for the both of you. If you leave the same point and end up at the same point, doesn't matter which pathway you took, you had to have the same drop. Okay? So if you go on a run and you start on one place and you finish at another, you go a different way than somebody else, right? And they say, oh, my way was so hilly. Well, yes, it might have had more ups and downs, but you would have had a lot of downs too, okay? Because the difference between any 2 points, no matter what the pathway, has got to be the same. So that's where we get those 2 13s. Now, these are going to be easy to calculate. Look, I know, for this one, I know its voltage and I know its resistance. For this one, I know its voltage and its resistance. So all I have to do to calculate the current is use my favorite formula. V is equal to IR for each of those components. So look how many times I used that same formula. I used it for the totals, right? And then I used it for this individual one to get the 87. And now I'm going to use it turned around to get I2 and I3. So the current going through component number 2, this one, okay? The current going through component number 2 is going to be the voltage and the resistance in current number 2, and I have both of them, right? Here's number 2, here's the resistance, here's the current. Okay, so the voltage goes in the numerator, that's 13 volts, and the resistance is 10 ohms. So 13 divided by 10 gives me 1.3 amps going through number 2. Okay, what about I3? I3, I take its voltage, it also happens to be 13, and I divide it by its resistance, right? Use the same formula. I2, this is V2 over R2 this is I3 would be V3 over R3. So this, just like we said, is going to be 1/3 as much as that. So I expect this to be 1/3 of the other guy, because look, this guy's got a 10, this guy's got a 30. So let's see what we get. 13 divided by 30. There you go. 0.43. All right. Now, think about this. So put those two numbers in my table. 1.3 goes for R2. This is 1.3. And this one goes to 0.43. Okay. Well, look what happens. All the current is going through here, 1.74. All of that current comes up to the juncture. Okay? Most of the electrons go down this pathway here. 1.74 amps is coming, but they split. 1.3 go this way, and 0.4 go that way, right? Well, if some of the cars go this way and some of the cars go the other way, you have to be able to add them up. What's 1.3 and 0.43? Well, that adds up back to 1.73 instead of 7.4. So that's just rounding error. Okay, a teeny tiny bit difference. Okay, so this and this pretty much add back up to that, right? This and this come out to 1.43 versus 1.73 versus 1.74. So when I finish that, I finish my whole table, and you see now they come down through here. How much is coming over here after this turn? This is 0.43. This adds up to the 1.3 coming right to here. We move this up a little bit. Right, how much is coming down here? 1.3. Everything goes through here. So what happens when 1.3 and 0.43 get together? Coming back this side, now I'm in the full part of the circuit, not the parallel part. 1.74. They have to add back up, and zoom, they go all the way around. They go all the way around. So if I put my alternative version of this back up, I know that this guy has a 13 drop, and I have 1.74 coming all the way around the whole circuit, because there's only one pathway. 1.74, 87 plus 13 have to add up. So in series circuits, the voltages add up and the current is the same. So the current all the way through this guy is 1.74. Pretty boring. Okay? Ours is much more interesting. I got 1.74 coming out of here after my voltage drop of 87, splits up, then gets back together, giving 1.74, and that's what comes back into the battery, and zoop, the battery sends it back up to 100, right? If I was going to touch right here, guys, with my voltmeter, this side of the battery and this side of the battery, let me just switch those. My battery would read 100 volts. That's how much potential it has. That's the difference between the positive side and the negative side. Okay, I'm going to leave this up here, try to make it a little smaller so you can take a picture. But this is the calculated results for circuit number 4. The calculated results for circuit number 4 of the lab simulation. Okay, let me just make it a little smaller. Okay, so you can see everything. Okay, I have one more piece of information at the bottom. I got to go a little bit smaller. How's that? Okay, let me, just in case you want to take a picture, let me just autofocus it. Okay. How's that? That's the whole thing. I don't have anything lower than down here. Okay, thanks a lot. See you next time.